Is it visible, Vedant? Because I am running animation. Yes, okay. Actually, we have once again, I will repeat in 2 minutes. We have started the chapter static characteristics of the instrument, and there we are studying right now what is the accuracy in measurement. Definition and the brief description of all these static performance parameters that we are going to see one by one now. The first one is the accuracy. Once again, I am repeating. The accuracy of measurement system is defined as the closeness of instrument output to the true value of measured quality. The closeness of the instrument output to the true value of measured quality, and measured quality must be considered as per the standard. So however, in usual practice what happens, it is specified in the percentage deviation. Accuracy is defined in the terms of percentage deviation or inaccuracy of the measurement from the true value. Now there is one animation here simple that shows the vernier caliper, and it has measured the outer diameter of that component, and outer diameter of that component, it is shown here, I think 2.46. You can see the accuracy over here. Outer diameter, sorry, 2.47 centimeter. So this is the actual measurement of the that component, outer diameter of the component. But what is the actual diameter and what is the measured diameter? That percentage deviation we have to see. On the basis of that, we are going to decide whether measurement is accurate or not. Actual diameter and measured diameter, there should not be a more difference. There should not be a more difference in order to maintain the accuracy here. Now we will see. So for example, that I have told you right now, but we will see this formula for measuring the accuracy. The accuracy of instrument can be specified in either of following forms. So percentage of true value, that is equal to measured value minus true value multiplied by 100 and divided by true value. Measured value minus true value multiplied by 100 divided by true value. So in this way you can calculate the percentage deviation or percentage of the true value that you can calculate. Or there is second way, percentage of full scale deflection. So measured value minus true value multiplied by 100 divided by maximum scale value. That is also one way to measure the accuracy. So accuracy of common laboratory micrometer, that depends on the instrumental errors like zero errors or errors in the pitch of the screw or anvil shape, etc. And in the measurement process, errors are caused due to the temperature variation effect. So this is actually uncontrollable parameter in some application or applied torque also. Sometimes what happens, when you handle the micrometer, you rotate the anvil or rotate the screw, at that time unnecessarily more torque is applied, and because of that also there may be the deviation in the true value. So we have to control a little bit of the temperature so as to maintain the accuracy, or while handling the instrument also we must be careful in order to maintain the accuracy. Now let us see. Just 1 minute. The next parameter of static measurement, that is the precision. Now please understand this definition very carefully. What is the precision? And we must understand the difference between precision and accuracy. So precision is defined as the ability of the instrument to reproduce a certain set of readings within a given accuracy. I am repeating the definition again. A precision is defined as the ability of the instrument to reproduce certain set of readings within given accuracy. For example, if a particular transducer is subjected to an accurately known input, and if the repeated readouts of the instrument lie within, say, plus or minus 1%, then the precision or alternative precision error of the instrument would be stated as a plus or minus 1 इंस्ट्रूमेंट. एक सिंपल लैंग्वेज में आपको बताता हूं मैं. अगर आप एक ही इंस्ट्रूमेंट से बहुत सारे रीडिंग्स ले रहे हो, फॉर एग्जांपल यू आर टेकिंग 50 रीडिंग्स बाय यूजिंग ओनली वन इंस्ट्रूमेंट, and in that 50 readings you have observed that the accuracy is plus or minus 1%. Accuracy is plus and minus 1%, and it is repeated again and again. तीसरा रीडिंग आपने लिया है, 15th reading you have taken, 20th reading you have taken, and you are observing the repeated accuracy in the reading. That is called as the precision. That is called as the precision. So once again I am reading this definition. So precision is the ability of the instrument to reproduce a set of readings within a given accuracy. In other language, we can call it as a repeated accuracy. In short, we can call it as a repeated accuracy that can be called as a precision. In short, we can call it as a repeated accuracy. So thus, highly precise instrument is one that gives the same output information for a given input information when reading is repeated a large number of times. अगर आप एक ही माइक्रोमीटर यूज कर रहे हो फॉर 8 hours, you are using same micrometer, you are taking thousands of reading and you are observing the same accuracy again and again, or same deviation in between true value and the measured value, that can be called as the precision. So precision is very important in order to maintain the accuracy. एक बार रीडिंग लिया, एक्यूरेसी आपकी अच्छी आ गई, ठीक है, प्लस और माइनस 1%. दूसरी बार लिया रीडिंग, तो उसके बाद भी आपने एक्यूरेसी जो है वो प्लस और माइनस 1% आ गई. तीसरी बार, चौथी बार, 100 बार अगर आप रीडिंग ले रहे हो, फिर भी वो एक्यूरेसी जो है वो मेंटेन रहनी चाहिए. दैट इज सिंपली कॉल्ड एज द प्रिसीजन. Now we will see a simple example here. I have taken this animation from Google itself now. So MT indicates measuring tool. Then MP indicates measuring platform. TS indicates a tracking sensor. IPS shows internal position sensors. And AS shows the actuation system. This is the robot arm here. This is the robot arm, and this is a supporting frame. And this X versus T shows the measurement of the vibrations you can observe here. So vibrations are measured over here, and these are repeated with respect to time. You can see again and again. So displacement with respect to time, the same type of response is observed over here. Same type of response is observed over here. So X suffix S. So this is the distance X REF. This is the distance. Here it is shown by dotted line. Here you can see faint black line. It is shown by XS. Then dark red line X suffix P. So this is the distance, and all these things are repeated again and again. There is no change in the nature of the graph. There is no change in the nature of graph. So displacement nature is constant with respect to time. Please understand my word. ये जो डिस्प्लेसमेंट का जो नेचर है, ग्राफ का जो नेचर है विथ रिस्पेक्ट टू टाइम जो वेरी हो रहा है, ये सेम है, उसकी क्वांटिटी भी सेम है. So this can be called as a precision in measuring the vibration. This can be called as a precision in measuring the vibration. अगर आप FFT एनालाइजर यूज कर कर एक प्रोजेक्ट कर रहे हो, नहीं तो रीडिंग्स ले रहे हो, तो उसमें अगर आप बेरिंग का वाइब्रेशन मेजर कर रहे हो, तो बेरिंग इज रोटेटिंग एट 300 rpm and you have mounted the probe on that bearing surface and you have measured its vibration. अभी 10 मिनट के बाद भी अभी वो बेरिंग जो है वो 300 आरपीएम पर रोटेट हो रही है, फिर से आपने प्रोब माउंट किया है, फिर भी वही रीडिंग दिखा रहा है. अगर 10 घंटे बाद भी ऐसी ही सिचुएशन में आप रीडिंग ले रहे हो, फिर भी रीडिंग वही दिखा रहा है, दैट कैन बी कॉल्ड एज द प्रिसीजन इन द एक्यूरेसी. So this is just a example. Actually, you do not need to draw such example in your examination. This is somewhat typical. You can mention simple example. Just I told you. So precision is the repetition of the accuracy. Just remember this. Precision is the repetition of the accuracy. Now in this, actually in this structure, TS shows the tracking sensor. It tracks the displacement. Then that displacement, actually it is calibrated, and these sensors are also used for the tracking the displacements. Sorry, I will see the next. Precision of the instrument is in fact dependent on the repeatability. जो मैंने अभी आपको बताया, repetition of the accuracy, that is what it is told here. The term repeatability can be defined as the ability of the instrument to reproduce a group of measurements of the same measured quantity. It is made by the same observer using the same instrument under the same conditions. Please remember these terms and conditions. The terms and condition is that while taking a measurement, same quantity must be measured, there should be a same observer, there should be a same instrument, and there should be same operating condition. मतलब आपने पहले 10 रीडिंग जो है वो 35 डिग्री सेल्सियस पर लिए है, तो आगे के जो रीडिंग्स है, आगे की रीडिंग्स भी आपको वही टेम्परेचर पर लेने हैं. सो टेम्परेचर कंडीशन शुड नॉट वेरी, देयर शुड नॉट बी एप्लीकेशन ऑफ अदर अनकंट्रोलेबल फोर्सेस व्हाइल टेकिंग द रीडिंग. बहुत बार ऐसा होता है कि आई एम शेयरिंग सम प्रैक्टिकल एग्जांपल विथ यू. Many times our MTech students do their project in vibration lab. So what happened in the first month of their readings, they take the readings by using FFT analyzer. They calculate the natural frequency and they write their natural frequency values in their project report. And after 5 months, the same setup is there, person is same, and they are once again they are taking the readings of natural frequency, but there is a huge difference, and this should not happen obviously. So once again that student comes under tension, sir, my readings are getting wrong, I don't know what had happened. Before 5 months this was the natural frequency, now it is changed after 5 months. Because this happens because you do not give more importance to this condition. Observer is the same, but the measuring instrument that should be properly calibrated. Measuring instrument that must be properly calibrated, then same operating conditions must be there. What happens, in one room you are taking the readings of the vibration, and in another room there is some hammering work is going on, that also affect on your measurement reading. एक रूम में आप रीडिंग ले रहे हो, तो दूसरे रूम में कुछ ना कुछ तो हैमरिंग का मेंटेनेंस का काम चालू होता है, तो उसका भी इफेक्ट जो है आपके वाइब्रेशन मेजरमेंट पर पड़ता है. सो देयरफॉर देयर विल बी अ deviation in the measurement of natural frequency. So it is bound that you must take all the readings in same condition with calibrated instrument, and observer must be a same. So be careful about while taking the readings in experimentation. As mentioned before, the deviation in repeatability or the inconsistency in the measured value are caused due to random or accidental errors that I told you. दूसरे ही रूम में कुछ तो हैमरिंग का और मेंटेनेंस का काम चालू होता है, तो उसके वजह से आपकी रीडिंग में एरर्स आती है. That can be called as a good word, that is called as accidental errors that we cannot control. So be careful while measuring the instrument. Next, another possibility we will discuss. One possibility is that the person hits all the bullets on the target plate on the outer circle and it misses the bull's eye. This is the figure 2.1a. Is this figure visible to you? I will zoom that figure now. Just wait so that it will be visible to you. Okay. This is the figure, and here this is the target plate, and we want to hit the bullseye. We want to hit at the center, but sometimes what happen? We miss that target, and our target becomes this plate, outer plate, and this is what high precision with poor accuracy. ठीक है, अपना जो टारगेट था ये प्लेट हमारा टारगेट है, बट we could not hit the target, bullseye. We could only hit the target plate. मतलब आउटर सरफेस को हम हिट करने में सक्सेसफुल रह चुके हैं, लेकिन ये जो सेंटर है, इस सेंटर पर हमें क्या करना चाहिए था? हिट करना चाहिए था, मतलब उस पर हैमरिंग होना चाहिए था. देन सेकंड डायग्राम, व्हाट इट शोज. Second diagram. The second possibility is that the bullets are placed as shown in figure 2.1b. In this case, bullet hits are placed symmetrically with respect to bullseye but are not spaced closely. Therefore, this case of good average accuracy but poor precision. Now you can see this diagram. We want to hit the bullet on center, but bullets are hitted around this center or around this circle. So that can be called as a good or average accuracy but poor precision. Why poor precision? Because we could not maintain the accuracy. We could not maintain the accuracy in the first shot. In the second shot, the bullet is hitted here. In the third shot, bullet is hitted here, here. So there is a lot of deviation in maintaining the accuracy. Therefore, we can call it as a poor precision. Accuracy जो है वो हर एक शॉट की है, लेकिन same accuracy is not repeated. But same accuracy is not repeated. Therefore, we can call it as a poor precision. But here you can see precision is high, but accuracy is poor. What is happened in this diagram? You can see over here. This is the target plate, and here we have hitted, here we have hitted, here bullet is hitted. And what is happened? The repeatability in the accuracy, it is maintained. So that is what good precision but poor accuracy. And here you can say the precision is poor but accuracy is good in the diagram B. Now let us see the next case. A third possibility is that all bullets hits the bullseye and are spaced closely. As it is clear from the diagram, this is the case of high accuracy and high precision. You can see this diagram here, over here, diagram C. High accuracy with high precision. Bullet is hitted at the center of the plate. Also, its hitting is also repeated again and again. So the accuracy is also good and the precision is also good. Then you can see the diagram D, poor accuracy with the poor precision. यहाँ पर क्या हो रहा है कि बुलेट यहाँ पर हिट की है, यहाँ पर आपने बुलेट हिट किया है, यहाँ पर भी हिट किया है, यहाँ पर, फिर यहाँ पर है, यहाँ पर है. So we could not even maintain the accuracy and even we could not even maintain the repeatability of that accuracy. हमने accuracy भी maintain नहीं किया है और वो accuracy का जो repetition है वो भी नहीं maintain किया है. So we cannot call this condition good for measurement. So in the both way, I will say the diagram A and B are good for measuring the performance of the your measuring equipment. A and B are good. Condition C is ideal condition that is not observed in the practice many times. High accuracy with high precision that is not observed practically, but condition A and condition B both are observed practically many times. Now let us see the next parameter of static measurement, that is resolution. This is also a very important parameter. उससे पहले मैं आपको सामने एक केस डिस्कस करता हूँ. अब मोबाइल का जो रिजोल्यूशन है वो पिक्सल में मेजर होता है, जूम करते हैं ना आप उसको, तो रिजोल्यूशन से क्या होता है, आपका जो क्लियरिटी है, मेजरमेंट का जो क्लियरिटी है वो बढ़ जाता है. तो उसकी वजह से जो है वो मेजरमेंट की एक्यूरेसी जो है आप इंप्रूव कर सकते हैं. रिजोल्यूशन इज डिफाइंड एज द smallest increment in the measured value that can be detected with certainty by the instrument. Once again I am repeating, it is defined as the smallest increment in the measured value that can be detected with certainty by the instrument. For example, आपने माइक्रोमीटर से 2.31 mm का 2.30 का डायमीटर मेजर किया है. माइक्रोमीटर से 2.30 mm का डायमीटर मेजर किया है, लेकिन अब क्या हो रहा है कि माइक्रोमीटर जो है वो डिजिटल आ चुके हैं. तो वहां पर डिजिटल माइक्रोमीटर पर आपको रीडिंग कैसा मिलता है कि 2.3012 mm. 4 digits are increased, 2.3012. That reading you will see. So this is what smallest increment in the reading. Smallest increment. 2.30 mm डायमीटर ठीक है ना, आपने मेजर किया, उसका एवरेज निकला 2.30 mm है. लेकिन अगर उस मेजरमेंट में थोड़ा सा भी एरर आता है तो आप क्या लिखते हैं कि 2.3012 mm. दिस रीडिंग इज shown actually on the digital micrometer. So this is called as the smallest increment in the measured value. और ये रिजोल्यूशन जो है ये एक इंस्ट्रूमेंट की क्वालिटी है. रिजोल्यूशन इज कॉल्ड एज द क्वालिटी, गुड क्वालिटी ऑफ द इंस्ट्रूमेंट. अगर आप वो नहीं मेजर कर सकते हो तो आपका इंस्ट्रूमेंट जो है गुड क्वालिटी का नहीं है. Nowadays even smallest increment in the measured value, if it is shown by the instrument, that instrumentation has a good precision, that instrument has a good accuracy. In other words, we can say it is the degree of fineness with which a measurement can be done, with which measurement can be made. डिग्री ऑफ फाइननेस मतलब आप जितना भी स्मॉल मेजरमेंट कर सकते हो उतना आप करेंगे तो उसका एक्यूरेसी जो है वो मेंटेन रहेगा. जैसे कि मैंने अभी ही एग्जांपल बताया कि आप डायमीटर जो मेजर कर रहे हो 2.3012, इतना एक्यूरेटली डायमीटर आपने मेजर किया है, दैट इज कॉल्ड एज डिग्री ऑफ फाइननेस. अगर आप डिजिटल माइक्रोमीटर यूज नहीं कर रहे हो तो उसका जो स्मॉलेस्ट काउंट है वो स्मॉलेस्ट काउंट लेकर आप माइक्रोमीटर पर मैन्युअली भी मेजर कर सकते हो, लेकिन वहां पर स्मॉलेस्ट इंक्रीमेंट जो है वो हर वक्त आपको नहीं दिखाई देगी. समटाइम्स देयर मे बी एरर इन मेजरमेंट ऑफ दिस measurement of that component. A ruler with least count of 1 mm may be used to measure the nearest 0.5 mm by interpolation. इंटरपोलेशन मतलब क्या है कि आप एक इक्वेशन लिखते हो, उसको करो फिटिंग भी कहते हैं, जैसे कि y इज इक्वल टू mx प्लस सी. तो ये जो इक्वेशन है ये स्ट्रेट लाइन का इक्वेशन है. इस इक्वेशन ये इक्वेशन यूज करके आप जो मेजरमेंट का जो डेटा है वो डेटा आप वो स्ट्रेट लाइन पर फिट कर सकते हो, या पैराबोला पर फिट कीजिए, मतलब उसको सेकंड डिग्री कर्व पर फिट कीजिए, वहीं तो थर्ड डिग्री कर्व होता है दैट इज क्यूबिक कर्व, वहां पर भी आप डेटा फिट कर सकते हो. तो वैसे भी फिट करके आप अप्रोक्सीमेट वैल्यू जो है आप निकाल सकते हो, मतलब स्मॉल इंक्रीमेंट जो है वो आप हैंड कैलकुलेशन से निकाल सकते हो। इंस्ट्रूमेंट नहीं दिखाएगा आपको वैल्यू। स्मॉलेस्ट इंक्रीमेंट जो है वो इंस्ट्रूमेंट जब नहीं दिखाता, तब आपको ऐसे इक्वेशंस यूज करने पड़ते हैं, जैसे कि y इज इक्वल टू ए प्लस बी एक्स, वाई इज इक्वल टू ए प्लस बी एक्स प्लस सी एक्स स्क्वायर, वाई इज इक्वल टू ए प्लस बी एक्स प्लस सी एक्स स्क्वायर प्लस डी एक्स क्यूब। ऐसे बहुत सारे इक्वेशंस आपको यूज करने पड़ते हैं, और उसमें स्मॉलेस्ट इंक्रीमेंट जो है वो आप मैथमेटिकली कैलकुलेट कर सकते हो, एक्चुअली उसका इंक्रीमेंट आपको नहीं मिलेगा। Therefore, its resolution is considered as 0.5 mm. Highest resolution instrument is one that can detect the smallest possible variation in the इनपुट। सो इसी वजह से मैंने थोड़ी देर पहले जो डिस्कस किया था कि स्टूडेंट्स नेचुरल फ्रीक्वेंसी एक्सपेरिमेंट से निकालते हैं, और 5 महीने के बाद वही कंपोनेंट होता है, वही सिचुएशन होती है, फिर भी नेचुरल फ्रीक्वेंसी में थोड़ा सा डेविएशन आपको दिखाई देता है। इसकी वजह एक है कि आप जो इंस्ट्रूमेंट यूज कर रहे हो वो बहुत एक्यूरेट है, उसका रिजोल्यूशन भी है वो भी हाई है। Because of this only you can get the accurate results. So resolution is a good characteristic of the instrument in order to maintain the accuracy. Resolution is also called as a discrimination. On some instrument, instead of the resolution, this word is used discrimination. This is also very important word. Sometimes you may not see this word, you can see this word discrimination. You can see this one example also. IR emitter, infrared emitter and infrared detector. So this is measured for the measuring the condition of your eye diameter. This is the used for checking the number of your eye. So expansion and contraction of your eyeballs that can be measured by IR emitter, and IR detector is used for measuring the smallest count or smallest change in the your eyeball diameters. ये जो यहाँ पर डायग्राम है ये आई बॉल की डायग्राम है, और यहाँ पर IR इमीटर क्या करता है कि उसका जो मूवमेंट है आई का वो ट्रैक करता है, और IR डिटेक्टर जो है वो मूवमेंट यहाँ पर इंस्ट्रूमेंट पर दिखाता है। और ये जो डिटेक्टर है, ये डिटेक्टर उसकी मूवमेंट जो है वो नैनोमीटर में भी दिखाता है। इतनी छोटी सी इंक्रीमेंट भी जो है वो IR डिटेक्टर हमें दिखाते हैं। आप जब डॉक्टर के पास अपनी आंखें चेक करने के लिए जाते हो, वहां पर आपको उसकी जो डिफ्लेक्शन है, उसका मेजरमेंट है, उसका जो एक्सपांशन है आई बॉल का, वो आपको दिखाई देता है बिकॉज ऑफ ओनली इंफ्रारेड इमिटर एंड इंफ्रारेड डिटेक्टर। दिस इंस्ट्रूमेंट इज यूज्ड इन क्लिनिक फॉर मेजरमेंट ऑफ योर आई बॉल्स एंड देयर डायमीटर। तो ये पॉसिबल क्यों है? पॉसिबल है सिर्फ ये डिटेक्टर की वजह से, उस इंस्ट्रूमेंट का रिजोल्यूशन कैपेसिटी जो है वो बहुत अच्छा है। The resolution capacity of the instrument is very good. Because of that only you can even see the expansion of this eye in the nanometer also. The next property we will see here, threshold. Sorry, what is threshold? It is a particular case of resolution. It is defined as the minimum value of input below which no output can be detected. Once again I am repeating, it is a particular case of resolution. It is defined as the minimum value of input below which no output can be detected. मतलब क्या है कि आपकी यहाँ पर एक डिस्क दिखाई दे रही है आपको। ये डिस्क का जो डायमीटर है, सॉरी थिकनेस है, वो 2 mm है, और ये 2 mm जो वैल्यू है मिनिमम है। 2 mm के बिलो आपको आउटपुट डिटेक्ट नहीं होगा। 2.001, 2.002 और 2.003 these values can be detected, but below 2 mm you cannot go for the measurement of that value, measurement of that thickness. So 2 mm you can call it as a resolution, sorry, threshold. 2 mm value can be called as the threshold. मतलब वो इंस्ट्रूमेंट का एक लिमिटेशन है, आप ऐसा समझ सकते हो कि लिमिटेशन है। मेरा जो शाफ्ट का डायमीटर है वो 2 mm ही दिखाएगा, 2 mm के नीचे नहीं दिखाएगा। ये इंस्ट्रूमेंट जो है वो 2 mm से ज्यादा ही दिखाई देगा। So it is defined as the minimum value of input below which no output can be detected. It is the instructive to note that resolution refers to the smallest measurable input above the zero value. Above the zero value. So both threshold and the resolution can either be specified as the absolute quantities in terms of input units or as a percentage of full scale deflection. So both threshold and resolution are not zero because of various factors like friction between moving parts, play or looseness in joints, then inertia of the moving parts, length of the scale, space of the graduations, size of pointer or parallax effect. So because of this, threshold and resolutions are not zero. थ्रेशोल्ड्स एंड रिजोल्यूशंस आर नॉट जीरो। जैसे कि मैंने थोड़ी देर पहले आपको माइक्रोमीटर का एग्जांपल बताया था, तो जब आप डायमीटर मेजर कर रहे होते हो तो वहां पर भी फ्रिक्शन होता है, थोड़ा सा friction in between the tip of that micrometer and the surface of the component. So there is a little bit friction. Because of this friction, obviously there will be a deviation in the reading. So therefore resolution and thresholds cannot be zero because of this uncontrolled parameter that I told you. अगर आप भी कोई वाइब्रेशन मेजरमेंट का प्रोजेक्ट कर रहे हो तो वहां पर भी आपके रीडिंग्स में वेरिएशंस आते हैं, तो उसका रीजन एक ही है, तो फ्रिक्शन एक रीजन है, नहीं तो लूजनेस। अगर आप कहीं पर भी नट और बोल्ट टाइट करना भूल चुके हो तो वहां पर वाइब्रेशन जो है वो ज्यादा बढ़ जाते हैं, डैम्पिंग अच्छी तरीके से नहीं होता, तो वहां पर आपको टाइटनिंग करना पड़ता है। इनर्शिया ऑफ द मूविंग पार्ट्स, देन लेंथ ऑफ द स्केल, दीज आर द पैरामीटर्स बिकॉज ऑफ विच resolution and threshold cannot be more, sorry, cannot be zero. The next point we will see here, static sensitivity. What is the static sensitivity? Static sensitivity of the instrument is determined from the results of static calibration. The static characteristic is defined as the ratio of magnitude of response to the magnitude of quantity being measured. So once again I am repeating the definition. Static sensitivity of the instrument is determined from the result of static calibration. Static characteristic is defined as the ratio of magnitude of response to the magnitude of quantity being measured. तो यहाँ पर स्टैटिक सेंसिटिविटी जो है उसको स्केल फैक्टर भी कहते हैं। अगर आप ने 2 mm डायमीटर मेजर किया है स्पेसिमन का, और आपने वैसे भी वो स्पेसिमन की जो क्वांटिटी है मतलब 10 टाइम उसका डायमीटर मेजर किया है, तो देयर यू कैन कॉल इट एज अ 2/10, that can be called as a static sensitivity. Magnitude of quantity being measured, magnitude of quantity being measured मतलब उसको हम इनपुट सिग्नल कहते हैं। So static sensitivity is denoted by K and it is equal to change of output signal with respect to change input signal, change of output signal with respect to change of input signal. And this is one diagram here, it is shown, this is the specimen and on which the force is applied. So here input force with respect to the output deflection that can be taken for the measuring the static sensitivity or applied force and actually the resistance developed by the specimen that must be a same. But sometimes what happen, applied force and there will be a sometime deviation in the resistance, so static sensitivities जो है वो change हो जाती है. In ideal case, sorry, in practical case, a change of output signal and change of input signal will not be the same. In practice, practical change of output signal and change of input signal will not be the same. Definitely, they will be the different. The next characteristic that is called as the linearity. A linear indicating scale is one of the most desirable feature of any instrument. Therefore, the manufacturers of the instruments always attempt to design their instrument so that output is a linear function of input. Output is a linear function of input. However, linearity is never completely achieved, and the deviation from the ideal are termed as a linearity error. In commercial instrument, the maximum departure from linearity is often specified in one of the following ways. Now we will see the diagram actually independent of the input. If the deviation of the output of the instrument from the best fitting straight line does not vary with the input, we can see this diagram, output versus input, that is indicated by q naught. Here it is indicated by qi. Now here you can see this line, this is the actual calibration curve. This straight line shows the actual calibration curve, and here this is the maximum deviation from the best fitting straight line. तो ये जो ग्राफ है ये क्या दिखाता है, एक्चुअली मैं सिंपल लैंग्वेज में बताता हूँ यहाँ पर. आउटपुट मतलब आपका जो मेजर्ड वेरिएबल है, ये जो आउटपुट जो है मेजर्ड वेरिएबल है. इनपुट मतलब आप जो है ट्रू वैल्यू आप उसको कह सकते हो, कैन कॉल इट एज द ट्रू वैल्यू, एंड दिस इज द मैक्सिमम डेविएशन, and the base fitting or idealize the straight line, but this is never achieved. This is never achieved. We always achieved actually second degree or third degree curve. This is the actual calibration curve. Sometimes the deviation is less, sometimes this deviation is maximum, and that also reduces the accuracy. Then next, proportional to the input, you can see this is the input, this is the output. Once again, this is the ideal curve, and what is happened here, the deviation is increased, and this is what the maximum deviation. So this is the proportional to the input. अगर input यहाँ पर increase हो रहा है तो deviation भी increase होगा. Input increase हो रहा है तो deviation भी increase होगा. In short way we can call it as a, if you are increasing the number of readings, so you will get the maximum deviation. अगर 10 रीडिंग आपको लेने हैं उसके बजाय आप 100 रीडिंग्स ले रहे हो तो आपका डेविएशन वैल्यू जो है वो इंक्रीज होगा, तो वहां पर एरर जो है वो बढ़ सकती है और एक्यूरेसी जो है वो कम हो सकती है. उसके बाद कंबाइंड इंडिपेंडेंट एंड प्रोपोर्शनल टू द इनपुट. हियर यू कैन सी दिस इज द स्टैंडर्ड लाइन, ये जो है वो एक्चुअल कैलिब्रेशन कर्व है, और यहाँ पर इंडिपेंडेंट डेविएशन एट लोअर रेंज भी दिखा रहा है. इस लाइन, ये डॉटेड लाइन है, और ये भी डॉटेड लाइन जो है वो भी इंडिपेंडेंट डेविएशन एट लोअर रेंज दिखाता है. तो ये जो दोनों ही डॉटेड लाइंस है वो हमें डेविएशन दिखा रही है, प्रोपोर्शनल डेविएशन एट हायर रेंज. तो यहाँ पर हमें दिखाई देता है कि कॉम्बिनेशन ऑफ इंडिपेंडेंट ऑफ इनपुट, combination of independent of input and combination of proportional to input, ये दोनों ही केसेस जो है वो हमें यहाँ पर दिखाई देते हैं इस ग्राफ में. Then range and the span, you can see this diagram, see this here, the range, just 1 minute, there is some problem over the diagram. The range of instrument is specified by the lower and upper limits in which it is designed to operate for measuring, indicating, or recording the measured variable. Again, I am repeating, the range of instrument is specified the lower and upper limits in which it is designed to operate for measuring, indicating, or recording the measurement variable. अगर आपके पास टैकोमीटर है तो वो टैकोमीटर जो है वो मिनिमम 10 आरपीएम मेजर कर सकता है और मैक्सिमम 2000 आरपीएम मेजर कर सकता है. दैट इज कॉल्ड एज अ रेंज. In algebraic difference, so sorry, the algebraic difference between upper and lower range values, that is called as a span. मतलब मैंने आपको यहाँ पर एक एग्जांपल बताया कि 10 आरपीएम जो है वो 10 आरपीएम कैन बी मेजर्ड, मिनिमम 10 आरपीएम and maximum 2000 rpm. So 2000 minus 10, that is called that will give us 1919 rpm. That is called as the span of the instrument. That is called as the span of the instrument. So upper limit minus lower limit, that will give you the span of the instrument. Another example, the range of the instrument can either be unidirectional or bidirectional. तो 0 - 100 डिग्री सेल्सियस और बाय डायरेक्शन मतलब -10 to 100 डिग्री सेल्सियस. मतलब वो जो टेम्परेचर वो निगेटिव भी हो रहा है और पॉजिटिव भी हो रहा है. और इट कैन बी एक्सपांडेड टाइप 80 - 100 डिग्री सेल्सियस और 0 सप्रेस्ड मतलब 5 - 40 डिग्री सेल्सियस. सेम केस जो है वो हमें प्रेशर प्रेशर पैरामीटर वहां पर भी हमें दिखाई देती है. So simply you can call it as a range, that is upper and lower limit, that is called as a range, and the difference between upper and lower limit, that can be called as a span. The over range of the instrument is the maximum value of measurement that can be applied to the instrument without causing a perceptible change in its operating characteristics. Further, the recovery time of the instrument is amount of time elapsed after the removal of overload conditions before it performs again with the specified tolerance. The next, selection of the instrument, how to go for the selection of measurement instrument. The selection of any measuring instrument uh, out of these available depends on the performance characteristics of the each instruments via its cost. In general, the selection procedure seeks to the maximize the payoff ratio or the transfer function of the investment, which is the ratio. So value of useful information or necessary total cost. The accuracy and the precision characteristics, including other specifications like sensitivity and linearity, then hysteresis and zero and sensitivity drift and deadband, these parameters you have to take into consideration while selecting the instrument. Nature and the type of data available, that is whether analog, digital or continuous or sampled. This also you have to consider. Then nature and type of readout, whether indicating or recording type. Then nature of the further data computation, that is also if required you can take the nature of further data for computation. Then signal to noise ratio, that also we have to measure. Then dynamic response characteristics, if input signal is time dependent, that also we have to see. Actually this point we are going to study separately in dynamic characteristics. So rest of the things that we will discuss in detail. Actually this point, selection of the instrument, that we will discuss once again in the depth after we learn the dynamic characteristics of the instrument. So this was about the static characteristic of the instrument. तर हे जे पीपीटी आहेत हे पीपीटी मी आपल्या मूडल वेबसाईटवर ठेवतो आहे आणि